I will introduce you to the narrowband technologies. Many of you, if you are the second or third time, has seen already part of the presentation, but has some new information about in how these technologies will be integrated in 5G. So this is the content. Let's start first with presenting an overview of existing wireless technologies. So from left to right, we have like short-range technologies, and on the right side we have cellular. So they need a SIM card service, or not like LoRack Sigfox. Those technologies that are low range, high range, means over 5 over 10 kilometers, compared to local area networks that are below hundreds of meters, usually below 100 meters. So if we go on the right side, we see that we have two types of technologies. We can split them in licensed and unlicensed. All these four technologies are low power wide area technologies. So it means it consumes low energy and it can transmit signal to distances of over 5 over 10 kilometers. Licensed and unlicensed is a very important parameter to take into account when you choose a network, because if you choose an unlicensed network, then all the network setup it's on your side. So you need to power up, for example, the antennas. If power drops or something happens, you need to fix it. But on the other side, with 3GPP licensed technologies, this is the job of the operator, and you just pay a service like a subscription, and it's their job to keep the connectivity working. Before we go in deep, let's clarify why narrowband and what is a narrowband. For example, we have wideband in the left, which in the end of the range. So let's say far away if the sensors are far away from the antenna, the signal could be high. The noise can be higher than the signal, and then the model cannot communicate because the signal is not powerful enough to be detectable. But if we take the same power and reduce the band, reduce the spectrum, then we shape this energy to go further, so to reach above the noise level, and thus the data communication would be possible even over a longer distance. Compare this like a flashlight, like 1 watt flashlight, that it's okay, so you can see closely, like 10 meters. But if you use even 100 times less powerful laser beam, like 100 milliwatts or 10 milliwatts, this will reach further, much further, hundreds of meters away, but still the beam is narrower, so you cannot see much, but at least it can reach much farther than a normal flashlight. So this is the difference between narrowband and wideband. Let's start at the beginning, why we get to this narrowband. So in the beginning, there was 2G, and the GPRS service sent data over the cellular network. Then things evolved, and Edge was here, so we have higher data rates. Then 3G and new technologies like HSPA with increased data transmission rates and dedicated data channels. So 2G, for example, it was possible only to have data and voice one at a time, while in 3G, we can have this in the same time. And of course, 4G or LTE, which means long network evolution, which made it possible for high-speed streaming, and all of us are using today capabilities of 4G for YouTube streaming, video, movies online, and stuff like this. So the operators get their money from 4G now, from all the applications that need high data rates. And 2G and the low data rate, it's only used for industry, but still the industry has a lot of devices that work only on 2G. And in the future, we will have 5G. Actually, the future is also here. We also already have 5G. And for 5G, operators need to reuse some frequencies. Some lower frequencies are better because have longer reach, but those lower frequencies are now used for 2G. So they, on one side, on technical side, they need to get rid of 2G to use the same frequencies, the same spectrum, because the spectrum is limited, is licensed, and only a couple of frequencies of bands that they can use. And on the other side, on the commercial side, they don't make money from 2G like they do it from 4G and the later 5G. So all this old technology, it's expensive for operators to maintain, and they want to get rid of it, but they cannot do it like this overnight because all the industry devices based on 2G will need some way to communicate. So the 2GPP association that is responsible for cellular standards invented two new categories. When this will disappear, two new categories called NB1 and CAT-M1. As you can see here, 4G has more categories: CAT1, CAT4, CAT6. The higher the category, the higher the speed. So the new categories NB1 and CAT-M1 have lower speed, but are designed to replace 2G and 3G networks that will be soon stopped. For example, in the US, 2G is already stopped for some operators. And sooner or later, up to 2025, 3G will be stopped worldwide, then 2G, because existing devices on 3G could still fall back to 2G if they need low speed, and devices that need high speed that were using 3G before could use now the 4G, because usually newer devices with 4G also support 3G fallback. So in the end, we'll have only 5G, and 5G will include 4G. 4G will not disappear. So those new two categories that are designed for the industry use will still be available longer in the future, for a longer term. Those new categories have also some commercial names. LTM for CAT-M1 or EMTC. EMTC means Enhanced Machine Time Communication. So this one was the first that was developed from GPRS, from 2G. Then they also invented CAT-NB1 or NB-IoT. It's the commercial name, which means narrowband for Internet of Things. This one is specially designed for simpler devices like sensors. I will tell you more about it. Just wanted to remember this slide, that we have two new technologies, LTM or EMTC and NB-IoT. Now let's see how these technologies are integrated in the older technology, and for which applications will they be used. So if we go from left to right, like yesterday, smartphones, they have a CAT4 LTE and above. Currently, most smartphones support CAT4. This means speeds up to 300 megabytes per second download. CAT4 means up to 100 megabytes per second. All the operators usually offer CAT4 network connectivity. Smartphone devices, smartphones, mobile devices support CAT6 or even more. But of course, this is not used for the industry with a lower rate. Are used for data streaming, video surveillance, For lower speeds, current 4G networks still support Cat1, up to 10 megabytes of data. And this is enough for any application. Then two new categories were released in standard 13. Release 13 is a standard that specifies how the device and the network should behave. And 3GP defined those new categories and how it will needs to function in the cellular industry. So for this, they had in mind two new groups of end devices. For Cat NB1 or NB-IoT, technology is designed for devices that are stationary. You see here, speed of the device is below 30 kilometers per hour. So you consider this stationary, like water meters, parking machines, vending machines, street lighting. So all these, let's say, 10 or more devices are good for NB-IoT. Devices that do not move much from the actual installation. Because if they move, they switch to another cell, and the NB-IoT doesn't support the handover from cell to cell. If device needs to move, then we can use EMTC or Cat M1, which works okay with speeds below 130 kilometers per hour. This means smartwatches, healthcare devices, or any other type of devices that move. Of course, we can use it also for tracking cars or stuff like this. So for over 130 kilometers per hour. But in this case, connectivity might be lost. So all the technologies can work in all scenarios, but if the speed is higher than written here, then the connection will drop and the device will reconnect. In case of a phone call or video call, this is not accepted to have interruption while you're driving. So this is why such applications use Cat4 or Cat1. But for normal industry devices that don't need real-time communication, data connection interruption are allowed, and so could be used for this purpose. Narrowband is more special because it needs more time to attach to an antenna, to a BTS. So if you move from BTS to BTS, like say 5 kilometers per hour, like walking, or even with a bike, connection time is, let's say, average around 5 to 10 seconds, or less or more. So this time is not enough for the device to connect to the cell, because it will enter in the next cell area before it manages to connect to the last cell. So it will never connect, only when it will be stationary. So NB-IoT is not good for vehicle tracking, but it's good for asset tracking. Devices that move, but once stop, they stay there. So you can get their current position. Okay, you have questions here?
Yes, we have a question, but unfortunately not to this slide. It's for a slide before. It's important part of 2G's audio and SMS. How will be supported in future?
Okay, about audio, I have a next slide, and then I will answer also about SMS.
Good.
When they designed NB-IoT, they had in mind these four principles. So to improve the coverage, and NB-IoT has 20 dB more power compared to GSM. This means the range is extended about 3 times, or the signal can pass through 2 walls, because it was designed for water meters installed underground in basements. Then massive connections. So once we have every sensor with a SIM, this means we will have more devices connected on the same cell in the same area. So this technology must support more connections in the same time for a single cell. So technology allows up to 100K devices connected on a cell. Price, of course, if every sensor needs to have a SIM, it needs to be low cost. So at least the cost should be comparable to 2G if we want to replace 2G. And last is power consumption. Water meters, gas meters, such devices have no power supply, are battery powered. So they need to last 10 years of battery and transmit data during this time. You don't see here everything about audio because audio is designed only for Quectel. So Quectel supports all of the above and also all what previous supports by NB-IoT and also this. So lower latency, 10 milliseconds, 50 milliseconds. So latency related to LTE networks, 4G networks, versus NB-IoT that has a much higher latency from 100 milliseconds to even 10 seconds. Then mobility, M1 supports cell handover, so a device roaming from cell to cell when speed is below 100 kilometers per hour. This means connection is maintained, not interrupted, if the speed is lower than this and device moves from cell to cell. Supports higher speed because it has a higher bandwidth, and supports voice over LTE or VoLTE. Voice over LTE means digital voice, not analog voice like 2G. So to answer your question, we will not have analog voice from 2G in those two categories, especially we don't have it in NB-IoT. We only have it in Quectel. So only Quectel devices could support voice. We need to add externally a voice codec to the device. It's not integrated because most of such applications do not use voice, and integrating it would mean increased cost. And SMS is supported by both, especially by Quectel, but for NB-IoT, operators don't support SMS because SMS is related to CS domain, which means circuit switch domain. And data and all what is related to LTE, it's from PS domain, packet switch domain. So SMS is sent to a control channel in the CS domain, and for applications that don't support voice, this path does not exist. So it's supported only if the operator supports combined attach. Combined attach means device tries to attach both CS plus PS domains, but most operators don't support this. So from the device side, SMS is supported. From the network side, for NB-IoT, I don't know operators to support it yet, but for Quectel, it is supported and working okay in combined attach mode. About coverage enhancement link budget, what this means, it's that the range of the signal using Quectel or NB1 technologies can reach farther compared to regular LTE Cat1. In case of NB-IoT, it's almost 20 dB higher. They do this by repetitive transmissions. Let me show you the next slide. So here you have the colored object is a frame that sends data from device to the network, and there are 48 resources in this frame. So 48 slots to send data to the server, to the operator. In the repetition means use the same data for all those 48 resources, so at least one of them reaches the destination and it's acknowledged by the network. This way, this is the way they reach such higher ranges compared to normal technologies. But this also means the throughput is lower, because if you use the same frame to use redundant data, then you cannot send more data in the same frame. so the data rate is lower, but at least one piece of information has a better chance to reach the destination. There are 3 such levels, 0, 1, and 2, based on max coupling loss. For NB-IoT, for Quectel, there are 2, mandatory 0 and 1, and the third one is optional. Retransmission means same data, so same frame is retransmitted more times. So in a frame, data is redundant, and then more frames are retransmitted with the same information to make sure at least one reaches the destination. This is how they achieve the higher power, like the 20 dB. Actually, the RF power is not much more than regular LTE, but using such mechanism, they managed to increase the chance of the signal to get to the destination. When such technologies are deployed in current network setup, they have 3 possibilities. So if there is already an LTE network deployed in the area, operators can use the in-band method. This means in a regular LTE data frame, LTE band, which is 20 megahertz, they could fit 1 or more eMTC frames or 1 or more NB-IoT frames. So this means in the same time frame, in the same band, more devices could communicate compared to regular LTE devices. For NB-IoT only, because the band is very narrow, it can fit in the guard band between 2 adjacent LTE bands. So this is the guard band scenario. And also, if they don't have LTE, only 2G, band for NB-IoT, it fits the carrier of 2G. So this means they can use channels from 2G for NB-IoT. So any deployments existing now could feed at least NB-IoT. And if they have 4G deployed, they can also support eMTC operators. When we look at device complexity, Cat4 devices, let's take them as reference. We say that this is 100% complexity. Cat1 is a bit less complex. So I told you earlier that Cat1 could be used for all the scenarios for the industry. The difference is in complexity. So if you compare Cat1 with Cat-M, they could do the same job for sending data through the network, data from sensors. But because the complexity is much lower for Cat-M, the price is also lower than Cat1. So this is why customers push operators to use Cat-M, because for same application purpose, they have cheaper devices. And on the other side, operators don't understand why customers can't use Cat1. So this we need to teach them and to push them to deploy Cat-M networks. Cat-MV, it's even less complex. So yes, you can expect even less expensive. First, I will explain now how the technology works by comparing it to 2G. I think most of us know how 2G works. So when you power on the module from left to right, the device first needs to perform network registration. So first it searches for the proper cell. There's a negotiation with the network, then it attaches to the network, and then can transfer data. This search and attach phase takes some time, and this time consumes a quite amount of energy, because in 2G, especially when the device first searches for the network, it transmits with full power. That means almost 2 amps in current peaks from the power supply. Then when connected to the cell, based on the negotiation, then they can then lower the transmission level. But first time, it will transmit full power. Then after data is transmitted, device will enter in a DRX stage, which means discontinuous reception. Well, just listens, so does not transmit, just in receiving mode, listens for page monitoring. Page monitoring means data that is transmitted from time to time, only when those green parts are active from the network, and in the orange part, device sleeps. And then when you want to reduce the power the lowest, you need power of the device to cut the power. And in this phase, of course, device is not reachable. When you turn on the device next time, it needs to pass the same phase, network registration. So again, search for the network with high power and then this repeats. And because for a device that is stationary in the same area, connected to the same cell every time, it's a waste of time and energy to search for the network, for the same network, for the same cell every time and consume this power. So low power wide area networks have a different approach. So first difference is that higher maximum current is 250 milliamps. Typically it's around 200 milliamps or even less. So second difference is network registration is one time only. What this means that device searches and attaches to the network, same as for 2G, but with lower current. But once it's attached, it remembers the network information. This happens also in 2G, but the difference is that at the operator level, even if the device is disconnected, the operator level, it remains registered. So next time we will not have to do this search and attach again. So similar to 2G, it will transfer the data, enter in this DRX page, and then goes to PSM. PSM means power saving mode. Again, it's not reachable in this interval, but it will not shut down. It will enter in this mode by itself, forced by the technology. We don't need to send some signal to power off or something. So after some timers expire, I'll show you on the next slide, it will go to this PSM stage, where power consumption is very low, below 3 microamps, which is comparable to leakage current of the shutdown transistor we usually use in 2G applications. Then when the device wakes up next time, it will not do search and attach again because it's already registered. So it directly connects to the last cell, and then because it's a new device that's with POSIX technology, the network knows it, and internally in their database they maintain this information. So the device just connects. So there are only 2 stages: connect, disconnect, and one-time registration. So when device connects, it just does a short sync with the network. This is a means traffic area update. This is mandatory if time for the new connection, then goes again to page monitoring. If there is some data needed to be transferred from the device side, so sensor has some interrupt and needs to transmit a new data, it doesn't need to wait for the time to pass for the device to wake up when timer expires. Device can wake up anytime, send the data, and then go back to sleep again. There are some timers. So this DRX time is called idle time. So this is time while device is waiting for data from the network. And there is also a third timer called tau, traffic area update timer. This has a fixed value specified by the network, and those timers are specified in the standard. So this means idle has a fixed period. You cannot set idle for infinite. So you set a time for idle, and then after this expires, device enters automatically in PSM mode And then from this mode, device wakes up automatically after this third timer expires. Values of those timers can be requested from the device, but are negotiated with the network. This means device can ask for some value, but network will decide in the end if it will use value from the device or not. Then network will assign some other value, usually a default value. Because if each customer will, or if each device will request their own values for such timers, then the network operator will need to implement a server for just to keep this information, which device, which timers was assigned. So this means extra cost for the operator. So it's simpler for them, at least in this initial stage, to use same value for all the devices and ignore values requested by devices. This depends how operators implemented the network. If you want to extend this time, so normal DRX time, normal idle time is in the range of seconds. This means for a typical water meter application, you could set idle time for, let's say, 10 seconds. Then PSM time is in the range of weeks, let's say 1 month, because you want to transmit the water readings each month for billing. So the device wakes up automatically from those timers each month, sends the current reading, waits for 10 seconds for some data from the network, then goes to sleep again. If you want to change configuration for such devices, send some new timers or something else, or make a firmware update or something like that, then you would need to practically wait 1 month when the device wakes up by itself, because otherwise you cannot reach the device is sleeping. Then after it wakes up, you have 10 seconds to send a comment and for the device to reply. So if you miss this 10 seconds window in a 1 month interval, you need to wait for the next 1 month. So to overcome this, you could extend the DRX time, so the idle time, you can make it longer. But you can only make it longer by extending the time between the receiving windows. Usually this time is 2.53 seconds. So you can increase it up to 40 minutes in case of Quectel, or more in case of NB-IoT. For example, here are values supported by the standard. For Quectel, this time can be up to 44 minutes. So this means 44 minutes in idle mode, in orange mode. And device can then will wake up automatically and listen for the network each 44 minutes, and then go to this idle again. So this idle time could be extended up to 44 minutes. Then for NB-IoT, we could have up to 2.9 hours. So technically, we could not use PSM, let's say. So you could extend this time up to the next traffic area update, which is mandatory. So this timeout will occur anytime. We cannot disable it. We can only make the device reachable between those two blue transmit periods. So if we can make the device not use PSM, but remain in such idle mode permanently. Of course, there is a higher power consumption, because in DRX mode, consumption is about few milliamps compared to microamps in the case of PSM. They made some study, so they compared normal mode when DRX is 2.5 seconds, and if you increase this time to the maximum, you could reach power consumption like 5% compared to normal mode. So this is also a way to compromise the lower power, but to keep the device reachable more than when sleeping for a longer time. The inactivity timer. Here you can see a real current measurement, what happens during a device wake up and when it connects to the network. You can see on the left side, the power on. From power on to network attachment, there is a lot of time, seconds here. So these seconds mean energy is lost. So first there is a negotiation of the network, searching the cell, then attachment, then transmission the data. And then it's a period of inactivity. Device doesn't do anything. Then it will release the connection, go to idle, and later to PSM. So if it's a sensor that only pushes data, you would want it to sleep immediately after transmission is completed. So after TX data. But this inactivity period cannot be set or changed from the device side. Usually it's about 10 seconds. This is a normal value for most operators. Some even have 20 seconds. But even 10 seconds, keeping the device alive with consumption in this mode is 60 milliamps, so quite a lot. Doing nothing, it's a waste of energy. So to overcome this, there are two ways. First question is, why is this here? So the standard allows a way for the server to reply to the request. So TX data is seen as a request, and then a reply should be arriving. So this time is reserved for the reply from the server. But if you don't need reply from the server, you can specify this when you send the data. So there are some flags. If you don't set the flags, it will behave like shown. If you set flag to 1, for example, you send to inform the network that this is an upload only packet and no download is expected. So you don't expect a reply. And in this case, after transmission is completed, device will jump directly to RRC release. So we'll jump over this inactivity time, then idle and PSM. So this is what you want in such application. So it's possible. Or if you expect a request, you set the flag 2, which means one upload packet and one download packet expected. So let's say the reply is received here in the middle or sooner. Then after the reply is received, it will switch, it will skip to RRC release phase and idle and PSM. So it's possible to improve such scenario depending on the application. If this wouldn't be, if this mechanism would not be implemented, then it could take more time for the device to wake up, attach, and then get the reply from the network. So this is somehow a compromise that you can configure based on your application. About communication latency in NB-IoT. Latency is let's say the biggest disadvantage in NB-IoT compared to all our other advantages as described. And it was designed like this. Actually, it was designed like this to support the other parameters, but this is the downside. So it's dependent on transport block size. So if you send small data in higher block sizes, this latency is bigger. This depends how the operator sets up the network. Number of repetitions, so this is depending on the signal quality, how the operator deployed the network, and only the fourth parameters are in users control, so EDRX and PSM, but also this could be forced only by the operator. So depending on this, latency can be from 100 seconds to 10 seconds. Typical application for NB-IoT uses UDP, so data that is not acknowledged by the network, because there will be no problem if some data is missed by the network. Device could send more data to make sure at least one packet is received. If we need the confirmation from the network layer, like when using TCP, this is also possible, but there are some drawbacks. One of it is that the context is slow start waking up from PSM. So if you open a socket, if you wake up from PSM when using UDP, the socket is still active, and you can still receive data without requiring to open a connection first, so less time to waste. But with UDP, this socket is lost, the context is lost. Second is that TCP will consume more power because for each message you will have an acknowledged message back. And the third is that if the PSM time is longer than the keep alive time of the server, the connection will be closed from the server side, and then the module wakes up and doesn't know what happened. It needs to reopen the connection again, which takes time. And usually keep alive time from the server, it's in range of minutes, hours, while PSM time is a range of days, weeks. So this condition will only be not satisfied. About new categories that will be used, some of these are already available. So as I said, the release 14, the standard specified how the device will use the bandwidth, what is the peak rate, what type of reselection is supported, like none of or more for CAT-M compared to NB1. Release 14 is a newer standard already deployed with some operators. So devices are called CAT-NB2 and M2 compatible. That mainly support higher bandwidth, higher data rate, better mobility, and lower latency. Let me summarize in next slide. We'll also have release 15. So those two releases will add some more improvements if we relate only to eMTC or CAT-M. It means enhanced voice and better mobility. For NB-IoT, means increased cell extension or support TDD, transfer data in time frames compared in in opposite now they use the frequency frames. And what is common is single cell multicast for both. This means when you do firmware update, you can broadcast same data to multiple devices, and lower latency, higher data rate, and device positioning. This one maybe would be more interesting for your application. This means the device can get timing information from nearby cells, send this information to the operator, then operator can compute the position of the device with 50 meters accuracy. This depends on how dense the network is, but still 50 meters for some applications is enough. And the advantage is that you have position without using GNSS, so with lower device cost. Such service is not available on the device, so the arrow is only from device to the network. So this means you need to pay the network, the operator, some additional cost for such service to provide the location of the sensor of the device. All this will be integrated in 5G. So I want you to understand how this will be included in 5G. So current NB-IoT and CAT-M devices will also work in the future without any change. So we migrated from 2G to NB-IoT in release 13, and now we'll migrate from release 13 to release 15, which means 5G. 5G, I will just mention that has, let's say, 4 main domains. You all heard about 5G, like fast speeds and high data processing. So this means, for example, eMBB, enhanced mobility broadband. So when you stream videos, high speed, high resolution. Then EUR LLC, which means ultra reliable, low latency communications. This is related to remote controlling robots for remote surgery, for example. So low latency and fast response devices. The last is V2X, vehicle to infrastructure. For example, cars can communicate between each other or communicate the traffic lights or the buildings. When a car wants to charge, it communicates with the building what type of parameters it has. So the charger from the building can provide the required current. And the third is in-band 5G new radio, which will include current LTE devices and will add more devices. How will they do this? Let's look at this spectrum image. So it's similar to the image shown in deployment case and some slides ago. This one is reversed. So we have here EMBB band. So this is the full bandwidth of 5G that can transfer videos or high data rates, high data that requires high throughput. On the same band, like LT included eMTC, also 5G will include eMTC and also NB-IoT. So the standard expects for such devices to be present in the network, and it will assign them a smaller band from all this 5G band. So such devices will still work as before in Cat-M and NB-IoT. So devices today can be used tomorrow when only 5G is existing, because 5G is prepared for this technology. 5G will not be prepared for 2G. This is why they want to replace it, but will be prepared for any LTE backward compatible technologies. There will be more releases. So release 15 from 3GPP now defines how the 5G network will behave. In release 16, this mechanism for integrating LTE-IoT devices is described, so in the middle. And release 17 defines more ways to use 5G for different applications, but 5G is not the purpose of this presentation. Okay, this was a presentation from my side for the technology. Now, if you have live questions or written, I can answer.
Okay, we have one. Is there data limit per day in NB-IoT, like, for example, Sigfox?
No, this depends on the operator.
Normally, it's the same like your mobile phone. You pay how much you use.
Okay, I hope it was satisfied. Now,
Or some operators are actually changing the business model from charging data to charging number of connections. So it can happen because the data rate on narrowband is very slow. So you are practically sending bytes. So you cannot even reach high data through narrowband. And that's the reason for cases like water meters, they will simply charge you connection. I don't know, €1 per connection per device, per month or per year, whatever. So there will be no data limit, but actually you will just pay for connection. It depends from operator how to build the business model. And to be honest, this is still the core problem of operators, because they are used to charge data, and in narrowband they cannot charge data because these are drops of water if you compare with water pipe.
okay. Next question. Could you add chipset information into specification file, or is it confidential information? This may help to decide which module to use.
For these questions, please come to the cells. Radu, I hope you will show also modules roadmap.
Okay.
And here I can tell for every module which chipset is included. It's not confidential, but we are not separately writing it, so I can easily in the next presentation describe, or even Radu will show this which chipset is in the model. Is this okay?
Probably yes. I do not see any more question to this one. And I have last one from my emails. What do you know about EU plans to add Cat-M1 networks? Which country or providers are ready to deploy Cat-M1 networks in European Union?
May I ask this? Every operator with LTE network is ready from technical standpoint to launch Cat-M. Everything else is a business decision to switch it on or not. But sooner or later, all of them will need to switch on Cat-M, especially because in metering, electricity meters require Cat-M. So water meters and gas meters require narrowband because they are battery operated and need low power consumption. But electricity meters practically in every country require Cat-M, because through Cat-M you can upgrade firmware of the electricity meter, and also the data traffic on electricity meter is much higher than on water and gas meters, and that's why market require Cat-M, electricity meter market.
Okay. I don't see any hands. Or one more question. How many antennas will be needed for V2 X applications in 5G for transferring data?
Okay, this is a question for 5G, not this presentation. It depends on application. So I don't have exact answer for you. You can have another 5G workshop, and then we can discuss this there.
Okay, it's something that it's a challenge accepted.
Please send such questions to your sales Quectel representative or to SOS, and they will forward. And because in the moment this is not part of this webinar.
Okay, so we will answer this question when we'll have the 5G webinar. And one more question. Do you support non-IP communication for NB-IoT?
Yes, it is supported. This also depends on operator, but device supports this, all our devices.
Okay, so you still have 1, 2, 3 minutes to write your questions.
Okay, meantime, I can show you the modules chipsets. This is current deployment status of the network in the world.
Okay.
And these are the chipsets. I'm not sure it's written here. No.
Maybe Radu, are you planning to go through this presentation or not?
No, because I'm not sure we have
Okay.
time. I can show it, but not sure we have time.
Okay. Denisa, how much time
Yeah.
do we have?
We still have like we are not limited. So in case you need like
Super.
5 minutes, so
Super.
go
Then
ahead.
I will do quick roadmap overview. So as it's shown on this slide, Quectel is using in their low power wide area modules 4 chipset. So we have Qualcomm, we have MediaTek, we have HiSilicon, who is owned by Huawei, and Unisoc. Maybe Radu, if you can quickly jump to HiSilicon. Also, this presentation, Denisa, please share with participants. Because it's very good. It's very good presentation, but it's a little bit boring going through the whole presentation, because it's actually we can just read the specification, but I will now try to go very quickly through the models. So HiSilicon modules, everybody knows this BC95 and his smaller brother BC68. These are stable modules. In China, we are selling huge amount, between 1 and 3 million per month of these modules. Unfortunately, they are based on HiSilicon, which is owned by Huawei, and outside China, these models are not anymore well accepted. Huawei announced new chipset, Boudica V200. So in Q3, most probably Q4, we are launching 2 new models, BC 950V and 680V. These models, to be honest, looks very nice. BLE would be included and so on, but I'm afraid that market, because of Huawei taste, will not accept it. So let's see what you as a customer will do when these models will be launched. There is no other news from HiSilicon models. Can you jump to Unisoc, please? In China, please be aware that there is about 15 chipset makers for narrowband. Unfortunately, using this chipset is not very safe, because most of Chinese producers of the chipset don't pay any royalties, and you can run into trouble if you are using such a chipset. We tested and checked Unisoc, and this is one of Chinese chipset makers who is doing everything right, let's say, and that's why we decided to launch for outside also narrowband modules based on Unisoc chipsets. We have 2 now in mass production, 2 modules, BC92 and BC95. BC92, the advantage is that this is the only non-Qualcomm narrowband module with 2G fallback. And I would dare to say it's pretty price competitive. somewhere in the middle between $5 and $10 in this range. And yeah, it has 2G fallback. And BC65 is only a narrowband module. It's nice. I could say it's even slightly cheaper than frequently used MediaTek-based BC66. But again, it's a question. MediaTek chipset give you a lot of advantages, like this low voltage power supply. You can use open CPU. And I believe for most of applications, even if it's 20-30 cents cheaper, and of course it's below $5, then BC66, I believe BC66 is still better choice. But if you have really huge volume, I don't know, 100K, 500,000, then it's wise to consider this BC65 module based on Unisoc. Okay, maybe you can jump, Radu, please, to MediaTek. So in MediaTek, we have old, very widely used in Europe BC66. Most of you know the benefits. Also, this open CPU is very good. Customers like it. Now BC66 got a new brother, let's say BC66NA, which support Cat NB2. And because of this higher data speed, practically this is the only difference. And of course, it's slightly more expensive than standard BC66. Regarding price, if we say that BC66NA is in a $5 range, BC66 should be for a little higher quantity, or 1K plus, already slightly below $5. Okay, that's all from MediaTek. And then the last chipset vendor which Quectel is using is Qualcomm. Most of you knows this BG96, which is very stable in mass production. A lot of customers is using, because this is still worldwide stable chipset with Cat-M. And that's the reason why it's very popular in Europe, in US, wherever Cat-M is needed. Unfortunately, Qualcomm is not decreasing price, so this module is still about $10. Cannot be reached price below, so it's in I don't know, $12-13 price range. But Qualcomm made new chipset 9205. So we have here BG95 family. This is whole family. And BG95M3 is practically direct replacement of BG96. So it supports Cat-M, supports narrowband, 2G, and also GNSS. So as I said, we have a whole family of modules, and I believe if you have any need for Cat-M, then BG95 currently is the safest decision. Then if you don't need, for example, 2G fallback, you can very easily switch to BG95M2, which have a cut M and narrowband and GNSS inside. Of course, if you need only cut M, this is BG95M1, also including GNSS. Also, I don't know, $50 cheaper than every function. You can calculate approximately $50 drop down. What is very important in this family that we have for Hungarian market, especially BG95M4, which includes 450 LTE. I know there is a big campaign in Hungary from MVM. So if you need samples, go to SOS. They will provide you with demo board. They can give you samples. These are available. Then we have Power Class 3 model BG95M5. There exists also BG95N1, which is only narrow band. To be honest, this model based on Qualcomm only for narrow band is a little bit or really too much expensive. So if you need narrow band, definitely you go to, it's better to go to MediaTek BC66 or a Unisoc solution. Okay, then we have, based on the same Qualcomm chipset, BG77. This is practically the smallest cut M module worldwide, very small, about 16 by 16 millimeters. If you need small size, especially for handheld applications or smart watches and such things, BG77 is the right solution. It's in mass production, but please be aware this model don't have 2G fallback. 2G fallback you can get in BG600, which is slightly bigger, have cut M narrowband 2G and GNSS, and this module is actually backward compatible, pin compatible with our successor MC60, which is most frequently used 2G module for tracking devices.
Just a second, Thomas.
Yep.
I just got back to BG77 because I have a question to it. Is this module as safe as BG95?
Sorry, as?
Is this module as safe? Like
safe, yes.
As
it's
BG95.
Yes, they are both. I mean, everything what you can see here is safe except BC69. Radu will need to remove from this slide BC69 because we had a lot of discussion what to do. If you can see, BC69 is the same like BG95M2, only the size is different. And for now, we decided to remove it from the roadmap because it's not enough demand for it, and on the same time this function is covered in BG95M2 and the same time in BG77, and BG77 is even smaller than BC69. So BC69 is from this slide is removed, and we will need to update the presentation. Everything the rest, what you see is safe, is practically most of them are already in mass production. Okay, BG95 MF not, and BG95 M4 we already have customer samples, and we are launching now mass production very soon. Everything rest is safe, what you see here. Okay, so including BG77, no doubt. So my recommendation would be, if you need cut M, BG95 is the safest family. You have all alternatives, and depends from the market and customer requests. You can choose the right model for the right money.
Radu, should we mark the BC69 as not recommended for new design?
Yeah, we will anyhow in new slides is removed.
Do you have an official statement about BC69 or something?
Yeah, I'm not sure if we have official statement, but I can guarantee to you now that it's not anymore in a roadmap.
Because I can see in our system we have order for BC69, so we can tell the customer do not design.
Yes, yes.
Okay.
I'm sorry for this, but it happened, I believe, 3 weeks ago.
Okay, I do not see more questions. Thomas, would you like to continue with more slides?
Actually, this was the last slide which I want to describe, and I hope I satisfied the question regarding chipset included in our models, because yeah, this presentation is based on chipset, let's say.
Yeah, I just saw that Radu was quite busy answering questions, like 5 or 6 of them, so it's good. Okay, I do not see more questions. So anyway, if you still have any questions, so write to us, to SOS Electronic, and I will contact Radu or Thomas for the appropriate answers. As you, many of you already asked if the recording will be available. Yes, it will be. We will publish it. We will make some article with this, and we will go out with the content on social media and our newsletter and website, as usually free on demand. So follow us. Radu, Thomas, would you like to say something at the end?
Thank you for listening to us, and hope we can help you with your designs.
Thank you.
Yes, I will join Rado. Thank you, everybody participating any of our webinar this week. And you are welcome with any question to SOS or to your local Quectel sales guy. I'm responsible for Hungary, and most probably you know Vít Peterka, who is responsible for Czech and Slovakia, or Gregos for Poland. So in every country there is also a Quectel salesperson. You can go through SOS or directly, whatever you need. And also in every region we have, I would say, local Radu who are experts for answering technical questions.
Okay. Thank you, Thomas. Thank you, Radu. Thank you for presentations and for answering the questions. And as always, I'd like to thank you all who joined us during our event and stayed with us. This was our last session about communication network, but at the end of month, we are preparing a webinar about embedded systems with our partner ION. Follow us, and if you are interested, register. We'll be happy to see you here again. And well, I wish you a pleasant and successful day. Have a nice day. Goodbye.
Thank you, Denisa. Bye.
Thank you. Goodbye.